Okay, so for part 5 of the design project, let me open the the other thing is there's a rubric up here. So let me open the instructions first and we'll go through that. This is basically where you're doing a trade-off of your solutions, and then you're going to present the results. So how I want you to do this is this is actually the way you're supposed to do it. You're supposed to rank each solution one at a time, independent of the other solutions first. So let me also open the PowerPoint that I have. The PowerPoints aren't going to open up in the window, so I'll just open them on my computer. Design project. Hey, whoa. Oh, I'm in the wrong folder. Oh, weird. How do I keep going? Oh, geez. My bookmarks are all messed up. Here it is. I'm going to open a bunch of files here. All right. So come on, Zoom. All right. Oh, I have my criterion. Let me go back to this. So I have my criterion here: low cost to manufacture, lightweight, patentable, etc. And notice for this, I just put my solutions A, B, C, D, E. And I have a key down here that tells me which one each of these solutions are. And what I did is I ranked, basically hide these other columns, and I did this one first. I said, okay, the integrated microwavable gel packs, cost to manufacture. I gave it my best rank based on, you know, what I thought and you know, how I perceived this design in my head. And this is going to require some of these will require some discussion between people in the groups. But this could take a decent amount of time, especially if you go through it as a group and discuss things. And oh wait, like one of these solutions, for example, D, integrated flexible heat pipes. I thought this was a very unique solution. I had a patentability as 5, but then I did a quick Google search. So my second part here is use the internet to help inform your ranking if you need to. So for example, in my example, right, I'm using heat conduction. If I was talking about using the copper material versus an aluminum material, right, I wasn't sure which one's faster heat conductor, I can go to the internet and look it up. I can also look up my ideas. Like if I just go to the internet and Google heated gloves, I wound up finding various products out there. And one that I didn't expect to find was I typed in gloves and heat pipes, and I actually found a paper describing some work where they wanted to integrate heat pipes into a glove that was part of like a suit. So it would capture heat from your arm and bring it down to your fingers. So that was kind of neat. I was kind of surprised at that. So that's why I ranked patentability as a 1 on that. Anyway, you're going to do something like this. You're going to rank each of your solutions against your criteria. And I didn't spend a lot of time on this because I was just trying to get something out there for you. And I wound up with some products. I wound up with 3 solutions that were all pretty close to each other. This is the point where if you have one solution that can be ranked differently depending on how it's constructed, break it into 2 solutions. So maybe you have one solution that's made out of a certain material like metal, right? And the same solution could be made out of metal or plastic. But depending on how it's constructed, that's going to change the manufacturability or the cost. It's going to significantly impact the difference between your weights. So you can break those out into two and weigh them or rank them separately. Once each solution is ranked, compare the sum products between solutions. Are they what you expected? Go back, look at the rankings of each solution. Do they make sense relative to one another? So this is where you can go back now and you have all the solutions in front of you and say, okay, instead of just looking at them one at a time, okay, why did I rank? Maybe you forgot. By the time you got to the fifth one, you forgot what you said about A, and you realize, oh, you know what? E and A are very similar with respect to the weight. So I'm going to rank, say I originally ranked this a 1. I'm going to change that ranking to 3 now that I've had time to sort of process all these in my head. Now is the time to go and compare them. Okay, this is my top ranked one. What makes this one different? Are these differences significant? And this is the point where you can adjust them, right? You don't have to go through them one time and that's it. This is the point where you look at your results and you say, do these make sense to us as a group? Is this kind of what we'd expect? And go back and discuss your rankings. I've been in meetings before where we've ranked things. We use this technique for other things besides just design. You can use it for brainstorming ideas, for troubleshooting plants. Anyway, there's been plenty of times where we've done the rankings and we're looking at it, we're like, wow, that's kind of surprising. And we go back and we say, yeah, this makes sense. If you look at the rankings, and we look at these solutions or whatever the problems are relative to one another, these rankings make sense. But the point is to agree on them as a group. And, if there's some discussion, record that. Because part of the assignment is to, now that you've done this, you're going to choose the top 1 or 2 solutions. You're going to put a PowerPoint together. And I've basically given you this template here. So the template looks like this. Let me drag my PDF over to the other page. I'm going to just open it on the other page. All right. So you're going to basically, the first slide is going to be your problem name, your group name, your member name. You can delete these green boxes. Well, you should delete these green boxes for your own presentation. These are basically boxes just to tell you what to do. The presentation, I mean, you can use this format, but just know that all your group members need to talk about at least one slide. So each group member must speak, and the beginning slide and the last slide don't count. It has to be one of the body slides. So no, just, if you're not comfortable speaking, you can't just do the title slide, right? The title slide is not count as a legitimate slide for discussion. The first slide is going to be where you discuss your selected problem. What's the problem your group decided to solve? This is way back from, what was it, the second assignment, I guess, because the first one was picking your name. And you can briefly discuss the alternatives and why you chose the problem you did. This is, the results of DP2, right, part 2. And then you're going to talk about your critical to quality criteria. So we're not going to talk about how you chose your problems. We're talking here about what are the criteria you decided were important for the solution you needed to come up with to solve your problem of choice. So you can use your actual table, and there should be some discussion around here. What are the criteria you added, especially the ones that were not part of the original template? Why did, like I had a template that had all these on there, right? You guys submitted tables that had some different criteria on them. Maybe point out some of the ones that were important to you, right? Like some of these are ranked pretty low. Some of these are ranked high. Why are these ranked high? Why is this one ranked low, right? Discuss that. Again, you did all this work already. You submitted a memo for this. So you have all this stuff done. Brainstorm solutions, you just did this one. So solution, short description if needed. Again, so you want to keep the slide very, you don't want the slide very wordy. You want sort of a brief bullet points. And then you're going to talk about your trade-off analysis. You can paste your trade-off table in. Think about these type of questions. Was it obvious what problem or which solution was the best before you did the trade-off? What are the assumptions you had to make? What was expected? What was surprising? And then what solutions did you select to work on? So here you're going to down select your solutions. And then here you're going to talk about your selected solutions. So here you can verbally say it. And the next slide you can devote to discussing that. And then maybe you have a reference slide. Well, have a reference slide. So I'm sure you guys can come up with, just from briefly looking at the submitted brainstorming solutions, some of the solutions already exist. So you can list references, right? Is this similar to something on the market? Is this a solution that you think is novel? What type of materials, that you might have had to look at to figure out if the solution's feasible. I also uploaded a demonstration, a sample PowerPoint. So let's look at that. This is the one that cold fingertips in winter. So that was my problem. And unfortunately, I'm in a group by myself, so I'm very lonely. So my selected problem was that my fingertips, and many people's fingertips get cold in winter, even when we wear gloves. Some of the other problems I looked at that I rejected were that my nose gets dry in the desert, my glasses fog in the jungle, and these two were primarily because of my expected market size. And then sand gets in my shoes at the beach. And I discarded this because I thought, everyone's got sandals or bare feet, and this is something that I don't think I'm going to contribute much to. So notice how I went through this slide fairly quickly, but I gave a brief summary of these problems. Criteria critical to quality. So these are the criteria I chose to evaluate my solution against, right? And primarily I weighted these things: cost to manufacture, lightweight, patentability, and touchscreen compatibility. These are things I thought were important. I thought it was important to be able to have a low cost and a unique solution, so something that I could sell and get a reasonable return on my investment. Because if you're the only one allowed to produce it because it's patentable, then no one else can make that product, right? And then lightweight, I thought lightweight and touchscreen compatible were very important for users, because you don't want to walk around with gloves that are like lead weights, and you still want to be able to use your phone, right? A lot of people like to use their phone in winter, and this is a feature that's already available on existing gloves. I thought that aesthetically pleasing was important, but not like the most important thing. Durability, same thing. Ease of developing, uses existing technology. I thought this is important, but not the most important thing. And then these two options, right? These are all, I think, important for the customer and myself, but not like critical, right? They have to be top 5. And then environmentally friendly. I put this a 1 because I thought, well, I think most gloves are probably going to fall in the same category as most gloves. So I don't think I'm going to do anything that differentiates this, that I'm going to be able to advertise, these gloves are going to biodegrade for you, and people are going to come flocking to me because of environmental friendliness. All right, so then I brainstormed a bunch of solutions, and these are my 5 solutions, right? And notice I didn't put a lot of information on this slide unless unless it didn't seem obvious. So for example, gloves with integrated microwavable gel packs. This to me seemed pretty obvious, right? You have a glove, and you can talk about it, right? You have a glove that has, in certain parts of the glove, there's gel packs, that are integrated with the glove, and you just microwave the entire glove before you go out in the cold. And those gel packs store the heat. This one, I thought, well, this could use some more explanation. Fingertip heaters, right? Well, I envision this as a separate wireframe unit that fits inside a pair of gloves. Number 3, I actually changed the wording on this one. So if you go back, oh wait. Oh yeah, if you go back to my memo, you'll see this is called something else. I think it's like self-heating fabric or something. So I gave it a more descriptive name, self-heating friction gloves, but I didn't feel this was still descriptive enough. So I just talked about it here. We have a glove that it's made out of a material that generates heat by friction as you move your hands, right? So that's the idea behind this self-heating friction glove. Gloves with integral flexible heat pipes. A heat pipe is basically a type of it's a constructed, but see, what is it? It's typically a pipe with some material inside. It's a construction that transfers heat quite rapidly from a hot section to a cold section. They're used in industry. They're used in computers. They're using them now because they can move heat from one place to another very quickly. They typically consist of some kind of external shell, and internally there's some kind of wicking material, and then there's some kind of fluid in there that does the heat transfer. And that's a very basic description of a heat pipe. But if you made them flexible, maybe you could have some that go up into the fingers of the gloves. So notice how I have this here, this bullet, and I described it, right? I don't have a lot of words for you to read as a person sitting in the audience. And then finally, the last one is shaped instant heat. And I just put a description here. So you know those instant heat packets? I figure if you have conductive little fingers at the ends of those, so you have a packet that, and I'll hold my hand up, right? The packet goes in your glove, and instead of just being a solid square, it's got these little finger sections that go up into the finger sections of the glove. So what I did here is I did my trade-off analysis. So you saw the slide where I showed you these criteria and the weights, right? And then I showed you the slide where I gave you my brainstorming ideas. So all I did is I relisted them here, right? And I put them as letters. Now I could have put them as words up here. For some reason, I thought the key would be easier. I could have just made these columns a little wider and word wrap them. But this makes it a little smaller of a table. And one thing that was interesting to me is that the integrated microwavable gel packs and the self-heating friction gloves came out on top. Very close to that was the shaped instant heat. And what I wound up doing is I wound up looking at these two, A and C. And let's discuss those, the integrated gel packs and the self-heating friction gloves. One thing to notice here is, let's see, and I called this out earlier. Well, fingertip heaters, I thought ranked kind of low on being lightweight, which I had as a pretty important weighting. I also think they didn't weigh very highly on ease of use and developing and resistance to moisture. I thought maybe this could be a problem. So I ranked these sort of middle of the road here. And so that contributed, I think, to the lower score. Integral flexible heat pipes, they had a few drawbacks. I think the cost to manufacture would be high. I thought they were very unique, but then I found that one reference that said they weren't. And then ease of developing, I thought it was not so easy to develop this. So that's another reason why the ranking was a little lower on that. So I chose as my solution gloves with integrated microwavable gel packs. And here's where I can discuss the close but rejected alternative. So the self-heating gloves that use friction from movement. One reason I rejected this is because I thought, and I can go back to my table here. Now I could have put my table on this page again just to have it, I can go back and forth. Ease of developing. Does this use existing technology? Well, not really. I don't really know anything offhand that's sort of self-heating friction material. You know, what would I use besides what, cotton or polyester? I have to really look into that. I think that would take some time to develop. So that's one reason I rejected this one. I think the idea is interesting, but I think it's going to just take too much time to come up with something. And it's high risk for failure. And then instant heat packs shaped with conductive fingers. I didn't really think this was much of a differentiator based on you've got this little heat packet in your palm anyway to begin with. Now you've got to worry about somehow getting a heat pack in there that has these little conductive fingers that go up into your up in your glove fingers. So now it's like, well, how do I get these in there? Do I put them in there first and then put my hand? Do I put my hand in? And it just seemed a little cumbersome for the user. But notice when I rejected these, right, even though my rankings were fairly close, right, these two are identical in ranking, I still thought about this, and this is where the discussion as a group comes along. You've got these two solutions that are pretty close, three of them if you include E, right? Why are we choosing one of these over the other two, right? Now you've down selected from 5 to 3. Now's where you have the discussion as a group. What do we like and dislike about these from the standpoint of, you know, development or ease of use or, you know, other things like that. And that's where I came up with my selected solution, microwavable gel packs. And I personally did not spend a lot of time on the reference page. I just linked certain links. So if you click on, you should try to have at least one link of information for each concept. Particularly if you came up with a concept, you're not sure if it exists. It's fairly easy to Google these things. And I've got links here you can actually go to. They'll take you to a website. So like, I think this is just Amazon. I don't even know what's it doing. Oh, okay. Yeah, so this is just an example of instant heat. Where's my PowerPoint? Here it is. Gloves with integrated heat pipes. This is actually a paper from 2003. So you can see, right, the idea came up in 2003. The thing about patentability is your idea has to be unique, right? And if there's prior art, like even just a paper like this, someone can say, well, someone came up with this 10 years ago. You can't really get a patent on it. And then finally, now I'm not expecting you to go through each one of your references. I'm just expecting you to have some references at the end of the PowerPoint. So this is battery heated gloves. Sharper Image has some, you know, battery heated gloves. It looks like they have a, is there a, you can't see the battery pack. There's like a zipper for the battery pack here. So the reference slide and the title slide do not count as slides that you're speaking on for your time, right? So if you have 3 people in a group, let's see, this has 7 slides, including the reference and the title slide. You're looking at 1, 2, 3, 4, 5 slides. You got to break up 5 slides between 3 people or 5 slides between 4 people. Again, title slide and reference slide don't count. As I was going through this, I realized I needed to add a little bit more information online, but these are the templates. The instructions are here. The presentation template is here. That's the one with the green boxes. That's a blank template. Well, it's not blank. It's just it's more blank than mine. And then the sample presentation is the one I just went through as part of this instructions. And I'm recording this as a Zoom lecture, so I'll post this lecture under let's see where I'll post it. You know what? I could post it here. I'll find a place to post it. I'll make sure you have a link to it, so you can actually see me as I went through the presentation. There's a rubric here. Oh yeah, that's what I got to do. I got to add time to the rubric. You have to I forgot to give you time constraints in your presentation. I knew I forgot something. Let's see. So the rubric looks at formatting, organization, content, and preparation and presentation. So I got to add time to this rubric. So you should have slides that are fairly simple, 4 to 6 points per slide. I had a few sub bullets, but the point is that you should have legible graphics. You shouldn't have a lot of really wordy slides. You follow the template fairly closely. So I wanted to give you a template that gave you some idea of what you should, how you should present. Let's see, it has 5 body slides, a reference slide. Let's see. I mean, you can add another slide if you want. Like say you have 3 people and you really want to do 2 slides. You could break up, feel free to break up one of those slides into 2. Content. These are sort of, there's not like it's not like math where you can grade exactly, the right answer. These are sort of, do you have valuable material? Are you presenting the material well, right? Is the content valuable, right? Do you have the content there, right? If you skip over completely your criteria and weighting and don't discuss it until you actually get to ranking your solutions, that's missing some of the material. You should show your trade-off analyses. You should be able to explain things clearly. You should be able to answer questions as well. So that'll be part of a presentation, right? Have some confidence in your delivery. So you get confidence in your delivery by looking at your slides and running through the presentation, particularly as a group, a few times. So run through your own slide. If I were in a group and I were assigned slide 3, right, I would go through slide 3 myself and run through it a few times. And then as a group, we'd meet maybe once or twice just to, refine our progress as a group. Say, okay, make sure I'm going to talk about this, and then we're going to go to your slide, but then we're going to jump back, or, whatever, just so everyone knows their order. So you're not standing there during the middle of the presentation saying, oh, wait, I thought you're supposed to go. No, you're supposed to go. You should know where you're supposed to go in the order of presenting. And do your best to split them up as evenly as possible. The point here is that every group member should talk at least one slide. So, I don't expect you're going to say, oh, that we had 5 slides and 3 people, so everyone has to present, 3/5 of a slide. Don't do that. You can have 2 people present once, or 2 people present 2 slides and 1 person present 1 slide. But everyone should don't give them the smallest slide to present, right? The person that gets 1 slide, maybe they should have the more in-depth slide to talk about, right? So split it up that way. Yeah, so, and then the rest of these are just, as you decrease in, and I've got to come up with a presentation time. I forgot I wanted to time myself doing that presentation, but I didn't do that. So I'm going to look back and see how long I expect that you go through for a presentation. We'll probably split them up into 2 days. We've got 6 groups. So I'm thinking 3 groups on Monday, 3 groups on Wednesday of next week. So yeah, that was a long-winded explanation. Are there any questions here? No questions. All right, so it's 1:35. What I think I'll do here is go through the rest of the information I wanted to present last week, and then this Wednesday, hopefully I'll make it through, and then this Wednesday you guys can meet here, and you can work on your brainstorming ranking together. Let's see, you did this. Let me just see the number of slides I have. Yeah, 1, 2, I can make it through these. I think I talked about some of these already. Yeah, I did. I think I did talk about these. All right, so let me go through some of these slides. This is a messy table of a whole bunch of units. You shouldn't have a slide like this in your presentation. When I put these presentations together for classes, my intention is also that you're downloading these and you have you have them, you know, somewhat as a reference as well. So I don't feel too bad about putting a lot of stuff on one slide. But basically, this is a table of a bunch of different units, and you know, things like frequency, force, pressure, stress. A lot of these are based on, these are derived units based on our base units, right? So for example, a force, yeah, you know what, I remember discussing this slide now. A force is a Newton, but a Newton is a unit that's based on mass, length, and time, right? So these are the base units. So you can break everything down into base units. Notice some of these have like electric charge. This is amp seconds, right? We've got luminous flux is a candela, but illuminance, which is a lux, is candela per square meter, right? So this is basically how much luminosity you have in a unit area. Some of these are, obviously, some of these are the base units, like Kelvin, right? All right, so yeah, you guys know this. You have to add and subtract units that have the same, or numbers that have the same units. You can't subtract like inches from meters or millimeters from meters. You have to put everything in meters or everything in inches. Oh yeah, I went through this already. You can use the rules of multiplication, right? You can cross off dimensions. You can cancel them, right? Like, for example, here, mass cancels. And I think, I can never remember if T is time or temperature. Should be temperature. Oh, geez. And then the lengths also cancel. You wind up with the dimension of L. Let's see. Yeah, dimensionless. An equation is dimensionally homogeneous if you have both sides of the equal sign have the same dimensions. And you want to make sure your equations are dimensionally homogeneous before you try to solve them. Here's an example of volume, right? Volume of the frustum. The frustum is just the, if you take a right pyramid and cut off the top, that leaves you with the frustum, or frustum. And it's got a square base. So the equation for volume is basically h over 3, right? Height over 3 times this formula for the base b and the top of the base, little b, right? And you can see here, right, volume is units of length cubed. And these are length squared, and here, this is obviously length, so you have length cubed, right? You want to make sure the units match on both sides of the equation. That tells you if you're doing something wrong or not. All right, so I have some of these examples to go through. Dimensionless or dimensional analysis. And let's see, we want to determine fundamental dimensions of some of these. Let me find my PowerPoint here, my PowerPoint, close that. Oh, yeah, it's up in the learning module. Remember that formula sheet that I had in module 2? This formula sheet has down here the symbols for dimensional analysis. And we're going to use some of these symbols to determine. So we got mass, length, time, got temperatures theta, electric currents I, C is luminous intensity, and N is amount of matter. So let's look at these on paper. Let's start with density. Density is fairly easy, right? Density has units of kilograms per cubic meter. So this is just mass per length cubed, right? That's easy. This is the fundamental dimensions of density, mass per unit or per length cubed. This doesn't matter what system of measurement you're in, right? It's mass. Doesn't matter if you're in SI units, it's still mass over cubic length, right? Flow rate. In this case, I've got units of liters per hour. Well, liters is a volume, and hours is a time. So our units here, or our dimension, where is it? Our dimensions. Let's see. Well, volume doesn't have a dimension, right? Volume is not a basic primary dimension. Length is. Time does have a fundamental dimension, right? Time is in seconds. Now, we don't need conversion factors here. All we need to know is, are these units a fundamental dimension? And we know that time is a fundamental dimension, so we write T. Volume is a product of length times length times length, right? So here, the dimensions for flow rate are length cubed per unit time, or per time, right? And again, this doesn't matter if you're in metric or or English systems, right? It's in metric, it would be meters cubed per unit time, or milliliters cubed per unit time, second, right? Cubic feet per second, cubic feet per hour, liters per hour, liters per second, right? These are the base dimension of flow rate. Electrical resistance, this one's a little bit more complicated. We have some equations that you probably have learned in physics, or you are learning in physics. Electrical resistance is called, well, first we have an equation for voltage, and that relates voltage is current times resistance. Based on this, we can rewrite this as R equals V over I, right? We also have another equation that's power equals IV. And here we can rewrite this as V equals P over I. So if I combine these two together, this is an R, I get an equation for R. R is equal to power over current squared. Right, so I is current, R is resistance, V is voltage. Notice what I did here, I got rid of the voltage. And the reason I did that is because the units are a little easier to work with here. Power is typically in watts, so this is watts. And current is usually in amps. But this is squared, right? So that's what these, that's what the units are in SI, right? Watts per amps. So now we can take watts, and we can write this as, let's see, my conversion factor here. Where's my conversion sheet? Energy. Oh, here's watts. Let's see. Did I put? Okay, I put the equations in here for energy and electric, right? Power. P equals IV. V equals IR. I tell you what they are. Power is watts. Voltage is in volts. Current is in amps. Resistance is in ohms. But the unit you have here is power in watts. And oh, look, amps are a fundamental base unit, right? They're a primary dimension. They are the primary dimension for electric current. And the symbol also happens to be an I, which is why we use it as a symbol in electrical circuits. A watt is a joule per second. And a joule can be written as a Newton per meter, or Newton times a meter. And a Newton Where did I put the units of Newton? Oh, geez, I put it somewhere. Here it is. A Newton is kilogram meters per second squared. So let's go through that and expand this out on paper. I can find my paper. All right. So a watt on top is a joule per second. And I've already got amps under here. I'm going to write my I squared. All right, so I'm going to write this as a dimensionless, or is my, yeah, you know, this is a tough one because I appears up here as a variable. This is my primary unit, I, right, amps. A joule, I already said, is a Newton meter. So now I have Newton meters per second over I squared. A Newton is a kilogram times a meter per second squared. So I'm going to write that out first here, kilogram meter per second squared. And then I have meters per second next to it. Oh, actually, I just realized you guys aren't taking physics yet till next semester. So some of you have seen this, some of you have not. This is my Newton. And this is the meters per second. So now I actually have this in base units, or in primary units. What I can do now is combine things and see what I get. I'm going to combine this first. R is going to equal, I've got kilograms, I've got meters squared, and I've got seconds cubed all over I squared. So now I've got mass, I've got length squared. I'm going to bring my time down to the bottom. And I've got current squared. So this is resistance. In primary dimensions. Resistance, which is ohms, this is what an ohm is. An ohm is fundamentally mass times length squared divided by time cubed divided by current squared. That's fundamentally, these are the primary units that make up an ohm, or primary dimensions that make up an ohm. I think what I'll do is cover the next two briefly in class the next time. So we'll just do these two problems and then we'll break out in groups so you guys can, you know, discuss with your group. And then you can also ask me questions. If you as a group want to go off separately and join, you know, say you don't have a class after this and you want to work separately on some other call, you can do that as well. But come back Wednesday, we'll do these next two problems. And then you can break out in groups and work on part 5 of the design project. Any questions, concerns, or anything else?
Are we ever gonna be tested on something like the electrical resistance ohms? Because, like, I'm not gonna lie, I couldn't follow half of that.
Oh, okay. I'm going to test you on dimensional analysis. So I'll probably pick something that's not electrical resistance, just because it occurred to me, a lot of you probably haven't seen that before. And you're not taking physics now until, well, next semester, most of you. So I probably won't put any electrical on there. But I'm going to keep it, I'll keep it fundamental, like you might have to do something like density or flow rate, or I don't know, I'll pick something else. If I pick something, I'll also give you the units for it if you don't have it. So I'll tend to guide you. I am thinking of putting a quiz together on this for probably next week. So I'll put together, we'll do some more problems on this. I'll probably just give you guys some, well, it won't be a homework assignment you have to turn in, but I'll give you like example problems you can look at on your own as well. Maybe I'll just make a video of it because that'll be the easiest way to do it, with some more examples if you need them. All right.
Okay.
Yeah. So have a good Monday. Enjoy the rest of your day.